Hello everyone, and welcome to this video short where we're going to talk about binary search trees. Previously, we discussed the tree as a data structure. A binary search tree is simply a type of tree. Binary tree is a tree that each node has at most 2 children, thus the term binary. Search tree implies that we have some sort of imposed organization or ordering on the data stored within the nodes of our tree. Why do we impose order? Well, again, as we've learned previously in this course, when our data is organized, it will allow for more efficient retrieval and storage of the data. The same is true here with binary search trees. In particular, we can gain logarithmic time for both search and retrieval and insertion of data into a binary search tree. That is attained in the average case, but I should say, the worst case is still going to be linear. And that worst case has to do with the structure of the tree itself. So let's look at a few examples. How do we impose order in our binary search tree? Well, the binary search tree property is simply that every node in the left subtree has a key whose value is less than the root node of that subtree. What does that mean? Well, here the root is a 5, so everything essentially to the left or in the left subtree of 5 should have a key value that's less than 5, and everything to the right should be greater than 5. This is true for every node in the tree. So for example, 3, left subtree has a value of 1, right subtree has a value of 4. Right. So this is the binary search tree property. We impose order in the data stored in the tree. All right. So again, what does imposing order do? It allows us to guarantee search times that are logarithmic in the average case. So why average case, you say? Well, there are different cases in trees where you have n nodes. What can vary from tree to tree if each of those trees has n nodes? Well, the structure of the tree itself. And the search time is directly dependent on the structure, specifically the height of the tree. Again, the height of the tree is the length of the path from the root node to the leaf node that's furthest away. That is the longest path from all the paths that emanate from the root node and terminate at a leaf node. So here, again, if we're counting edges along the path, 1, 2, 3, the height of this particular tree is 3. Note that the number of nodes here that can be stored is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We could have 13, 14, and 15 nodes. Right, note that this is 2 times 2 times 2 times 2 minus 1, or 2 to the 4 minus 1. Right, note that this is directly related to an exponential growth with respect to the height, meaning that the path down here is logarithmic as compared to the height. Thus, we get our logarithmic term. Note that this particular search tree has a structure where it's not quite as balanced, and so we're going to get some paths here that are a little bit longer than logarithmic, and some paths that are shorter. Whereas if the tree is more balanced, many of the paths from the root to the leaf node are going to be about logarithmic. Note that there are some examples in this slide deck that show you trees that are not binary search trees. They either violate the binary property, meaning that each node has at most 2 children, or the ordering property, that is, the left subtree has a value less than the root node. Here are some counter examples. All right, so we can take a look at this. Is this a binary search tree? Right. Well, it looks like we're going to violate the ordering property here. All right, are these binary search trees? Again, note that this one here is a very extreme and interesting case of a binary search tree. Note that each node has at most 2 children. It is in fact a tree, it's fully connected, there are no cycles, and it does abide by the ordering property. However, note that the height of this tree is also equal to, essentially, the number of nodes in the tree, which is the worst case for a search tree, because the height, which essentially is going to be the search time, is now the same as n the number of nodes, meaning the search time is going to be big O of n, or linear. All right. So again, this indicates the worst case scenario. Average case for the average tree, and if you average over all possible structures of trees, you get logarithmic search time. However, worst case, with any arbitrary tree that's chosen, you could still have a search time that is linear. All right, well, thank you for joining me in this brief introduction of binary search trees and the time complexity analysis. I'll see you in the next episode.